Hello, I'm Dora Blanco. I'm full professor at the University of Santiago de Compostela and senior researcher at CITIUS, also here at the University of Santiago. This podcast is on the School of High Performance and Disruptive Computing in Remote Sensing that has been held here at CITIUS during the first week of June 2024. This school has been organized by the Earth Science Informatics Committee of the IEEE GRSS Society. 35 students of all around the world has been selected to attend this school. This has been supported by different institutions, universities, and other companies. For example, IBM, NASA, ESA, Google Earth, the University of Iceland, the University of Boku, and other institutions, including, of course, the University of Santiago de Compostela, and in particular, CITIUS. The objective of the course is to provide to the students knowledge on the recent advancements, basically on high-performance computing, machine learning, and quantum computing applied to remote sensing. Large language artificial intelligence models is one of the most relevant topics of the school. We have here two researchers very well known at the international level to talk about this topic. These are first Dr. Manil Maskey, who comes from NASA and who is also with the University of Huntsville, Alabama. The second one is Thomas Bruce Weiler, who is with IBM Research at Zurich. I hope you enjoyed this talk. Hi, both of you. After this long presentation from my side, the session that you lead in the school is designed to offer participants an understanding of the data life cycle in the field of geoscience and remote sensing, and provide the participants with skills and knowledge to tackle real-world challenges. And I have some questions for both of you. Manil, in particular, I'm sure that our listeners probably know what deep learning models are, but we should explain what foundation models are, and in particular, what are the geospatial foundation models provided by NASA and the potential benefits for researchers from these models to know more about you and this work.
Yeah, sure. First of all, thank you for inviting me to talk with you. It's a very unique situation to invite all of these global students to Santiago de Compostela. I think they're learning a lot, and happy to be part of it. So going back to your question, I think before I tell you what the foundation model is, maybe I should explain how is it different. Mm-hmm. So traditionally, the researchers have been using this supervised learning approach to build AI models, right? That's where a lot of success has happened in the last 10, 12 years. And the approach there is, given an AI application, you curate a large set of training data set, labeled data set, and you build a model, right? And it works really great. And we have had so many success within NASA and in industry, academic sectors. But what foundation model gives you is some of the pain points of building supervised learning, really related to training data generation and the generalization of that across multiple applications. Foundation model does not require training data set to train a model. It is a self-supervision approach, which means it learns by itself by looking at data representation. Mm-hmm. So ultimately what it does is, given a large corpus of data, it creates a data representation, meaning that it learns what the processes within the data are over time. So it's uniquely suited for time series kind of data. Mm-hmm. And once you have that data representation, you can tune it with very little supervision, very little training data set for different types of application. So the benefits here is that the cost of curating large amount of training data set is minimized. And also the resources required to training a new model is also minimized. So there's a wide range of benefits when you do that, right? And the types of application you can build is quite few, because when we built our foundation model with IBM Research, we didn't think of all the applications ahead of time, right? We only thought of few that we knew we had a proper benchmark for, but the community has taken it and built so many different types of application that we hadn't even thought of. So I think that's the benefit of foundation model work. I think the geospatial is a little tricky because the foundation model concept came from language model, which is sequential data, and you try to predict, you mask out the words and try to predict, right? So how do you translate that into geospatial data, which is much more complex? It has spatial coherence, it has time information, and it changes over time. You have multiple sensors. So that's the novelty of the work with IBM research that we did. And now what we're doing here is trying to teach people how to use it, right? It's fundamentally changing how we do AI for geospatial data. And happy to be part of the effort to teach community how to use it.
And reducing the computational load.
Exactly.
So it's a great benefit of these models. And you have also, tomorrow we will talk about large language models, generative large language models that are currently very popular as an artificial intelligence topic. And everyone has in mind tools based on large language models that ChatGPT and all these applications, very popular, especially during the last year or year and a half. And however, their application, the application of these models in geoscience is not as well known, and these models present new opportunities for analyzing the information from a different perspective, considering multi-source information. Could you explain how NASA is utilizing these models for scientific purposes and the specific tasks that they are being used for?
Absolutely. I think this is also work we did with, we started with IBM research. Actually, this work with language models started before our geospatial foundation models work started. So our community, when they do research, they publish their findings into scientific journals, conferences, right? So there's a lot of information embedded in those documents. So that's what our initial thought process was. Can we extract information from these scientific literature, publications, documents, right, technical reports, so that we can use that to do a number of different things, right? One, you can look at over trend, right? What people are using in terms of application, what data is useful for us, what kind of data fusion can you do to do different kind of applications. That's how we started, but it has evolved into a lot of these upstream tasks that we talk about, right? We get admission data, that's the start. How do you convert that into something that's usable by science teams in terms of data? Those are our data stewardship tasks. There's a role of language models there because there's a lot of mundane, repetitive tasks that human has to do.
Yeah, labeling and organizing.
Exactly.
And
metadata generation.
fusion of RGB information with SAR data.
So a lot of those repetitive, mundane human tasks can be made more efficient so that human can focus on truly creative things, right? And for example, we're using it to generate science keywords for metadata. So when you search for data, it does a better job of searching. We are actually using human language to search for data, right? I think the search paradigm has changed quite a bit. You see this in industry, how people are changing, like Google is changing the search. It's the same thing, right? People are not going to search in a couple of years by clicking keywords, right? It's going to change. It's going to be human-based, human language-based. So we're trying to focus in advance. How can we change our search mechanism? And that's where language model is also very powerful. And it's an evolving thing. We just recently released 2 models focused on information retrieval from metadata, right? When you look for some data, how can you return similar looking data without using the traditional database approach? And the other one is the science keyword generation. What we're using one of the models to see, because these science PIs, the principal investigators, they're not concerned about helping you with the metadata, right?
Yeah.
Search for the data. They
It's
took
very
the
boring.
data.
It's very boring.
Exactly. Yeah, they have better things to do. So all they give you is like, this is the information about the data. And it's the data steward's job to create proper science keywords so that when people search for data, they actually can find the right data. So 2 applications that we're currently using it heavily on. Ultimately, what we want to do, and it's part of the workshop tomorrow, or the summer school tomorrow, is to combine both geospatial and language model, right? Where you can actually show me all the fires in California, it can actually not only parse that information, right? It can do geospatial search, and then go into the inferencing of the foundation model and look at all the fire information that the foundation model can, and return it, right? Do analysis. So it can automate some of these analysis on the fly when you combine these two. So that's where we're going.
Yeah, increasing accessibility to data.
Yeah, and make it more efficient.
Yeah, more efficient. Yeah. It's very interesting. I'm also interested because in open science principles, because these principles are being encouraged by the European Research Council in Europe too, and very actively by NASA in US. And it's very good for universities, of course, to accelerate research and understanding. And how is open science promoted by NASA? Because this directly impacts research outcomes.
Yep.
Could you tell me? I think that it's a complicated question, but
yeah. So we have had the open data policy for 25 years or so, and recently we've been promoting or mandating some of our funded effort to be open from the beginning. So that's our intent, is to open from the beginning, right? Anything related to the science we do, we make our researchers make it open, including publications, models, any artifacts related to data, ancillary information, obviously the model training data set for AI work, right? And what has happened is there are institutions, like-minded institutions like IBM Research, who are on the same in terms of philosophy.
Yeah.
Right. And so open partnership is also one of the big efforts within NASA, to partner with like-minded organization to collectively join and do the work. And it has opened up the door for foundation model, because NASA alone cannot develop it, because there's a computational resource limitation. There's also AI expertise shortage, right? People want to work in government, but it's much more exciting for them to go to Silicon Valley and get 3 times the salary, right? So how do you engage with that community, right? The open science gives us a framework to work with, and like you said, it's a collaboration with ESA, European Union as well. There's a government level talk in terms of how do we collectively make things open and benefit the society, and there have been policies that has come out recently from NASA in terms of what does open mean, and how does it benefit, and what the researchers should do in terms of adhering to that.
Because large language models have a clear impact in this experience. Yeah,
absolutely. And this is one of the effort. The school is one of the ways. The training is also a component of that. It's not just open training like this, where you actually bring in communities that usually doesn't get a chance to be part of such an initiative.
Yeah.
To teach them how to do these things openly is also part.
And it's very good for us in particular at HDCRS, because we need access to data. So it's
exactly.
And we need to train the models with original data to at least
and with one of the example is we put the model out in the open in a Hugging Face.
Yeah.
And you can see the uptake in community adoption, new application, like I said. And also entities like Jülich Supercomputing Center, who sees the value in this and trying to scale it so that more people benefit from open models. Mm-hmm. So it's all benefits of open science.
Of course. Thomas, I go for you. IBM is a prominent company. We all know IBM here, with a robust research division, with the development of artificial intelligence solutions as a priority, as we have seen during the school. And the collaboration with NASA is clear at the school. We are seeing that you are both here collaborating. And your work includes the development of foundation models to accelerate the discovery of climate impacts that have social and industrial impacts too. Could you elaborate on IBM's objectives in this domain and your partnership with NASA? I have seen your developments in climate this morning, but I think that it's interesting to summarize these ideas here.
Yeah, absolutely. First also, thanks for inviting us here to this historic site and city. So it feels like really being on a scientific pilgrimage here. And also it's kind of nice to see the excitement of all the participants. Thanks for this. And yes, so kind of we want to have an impact kind of with our work, beyond LLMs. So we want to have, accelerate the scientific discovery. And in particular, the topic of climate change is really pressing. So, the globe is changing quickly. Society, we as humankind, we have to adapt. And so that's why we think kind of our work is really important, and we have to provide quantitative means kind of to assess the situation, kind of to allow kind of to adapt and kind of to also mitigate. And that's kind of where remote sensing and all these kind of weather and climate predictions are really important. So having said that, right, kind of let's say IBM with kind of a strong focus on computer science and AI, a lot of skills there. We also have quite diverse teams, also from physicists and environmental scientists, but still, kind of we need to engage, to have real impact, right? And that's kind of where partners like NASA and Manil's team is just like excellent, right? And, as well, kind of IBM is very much at heart kind of open science and related. So we have also initiated kind of in the beginning kind of this year, kind of the Open AI Alliance. Well, like worldwide, kind of 50 institutes are kind of participating, and it's growing, so that's exciting to see. And in general, just like also, let's say from the Zurich lab, we have a lot of engagement kind of with European universities, industry partners, etc. And also we have a public-private partnership, for instance, with ETH on site. So we just know from there, like if you get together, like it's more than the sum of the two parts. Yeah. So it accelerates really. And I think it's also an example, the school. Right, we can now see how the community is picking up the models, and this is only possible like with NASA, with ULIS, etc. And thanks to your invitation here. And so that's really key. At the same time, also, there's a business angle to it, right? So there's a business unit, and we want to provide through Watson X and then our environmental intelligence business unit. Kind of, we want to provide these services as a B2B company, kind of to our clients. So, this may be insurances, this may be, on-prem installations of AI platforms, for, entities operating satellites and also kind of later kind of exploring the data sets. So these are our customers, let's say at heart, but pretty much in the research space, we kind of collaborate with basically the world kind of to have really an impact. So, and open source has really shown that there's huge potential, while still being the potential kind of to also have a business. So I think that's the beauty, I guess.
Yeah.
So, and that was really mind-boggling. I didn't believe first, but like also with Red Hat being part of IBM, this is just like the nature, and also transformed IBM over times, and we're here together. I think that's great.
Yeah. And will a transformer-based model replace the traditional way of predicting climate in the future? Is the future because the model is working very well.
Right, exactly. So this is still a research question. I was just like at the last week in Geneva at the AI for Good Summit, and there we had a workshop just on this topic. Kind of together now with kind of the work with NASA, we have shown kind of on an AI model, a weather and climate AI foundation model trained on the MIRA-2 dataset. And it has shown that we can do downscaling, we can do forecasting, different tasks, also like for wind farms or solar farms. Having said that, that's kind of on a shorter term, maybe time horizon of 10 days. That's kind of the forecasting part. We can do the downscaling on climate data already, so that's very interesting, like if it's about climate projections, because typically, like these climate models, they provide you spatial resolutions in the range 25 kilometer or larger. It's a bit frustrating. There's like an example, I don't know, like as a Swiss, there's this Matterhorn, this beautiful chocolate mountain. And if you look at the models, it's flat. It's just like if you look at the weather forecasting, the Matterhorn is not resolved. So basically kind of the model we developed there, the downstream task from this weather and climate model, kind of can show that you can do a downscaling, meaning kind of increasing the resolution for precipitation or temperature by a factor of 12. And so this has a huge impact, and kind of if you start talking about urban planning, etc., like for the future.
Mm-hmm.
So
That's
I mean,
interesting.
yeah, exactly. That's one thing, and maybe if I can add an additional element, like I think the weather forecasting world had its ChatGPT moment, I would say, last year. So these AI models have shown that they can have equal skills in forecasting up to 10 days.
Yeah.
While the computation needed is like 4 orders of magnitude lower, like, more than 10,000x. And this is amazing. So compared to a cluster, you can run then kind of the workload on a single node. And this has big implications. So the question is like, can you now do it also kind of for these climate projections? Because kind of in weather forecasting, typically you assume in this decade kind of, the weather is more or less, the distribution of the weather is more or less the same. But for the climate, kind of, you talk about out of distribution forecasting.
Yeah.
And so that's kind of the current discussion, and kind of these models, they are being probed, how much physics is being learned by the models. So I think, it's pretty exciting times, I would say.
Very exciting.
Yeah.
I think just to add to what Thomas said, from science side, I think I mentioned this earlier, the efficiency gain is something that is unique for using the foundation model approach, right? It is mentioned how it requires less computation to do equal or better. That's just one task. Foundation model can do multiple different tasks, right? It's not just forecasting. I think there's only one other foundation model for weather called Climax, I think, from Microsoft. So this is unique in a sense that now the community can do multiple different things much faster at much higher resolution. I think those are added benefits of doing climate research.
Exactly. That's kind of what you're saying is actually kind of very important. Kind of, exactly, I mentioned these 4 orders of magnitude improvement. That's only for inference.
Right.
But then we still state, to build these models. And I mean, it's true, right? We need large clusters.
This was my next question.
Right, okay, right.
High performance computing is necessary because we need to train the initial models, and you need supercomputers to train these initial models, as we have seen this morning. But it's interesting to say that we need first to train the models, and it's very costly. But you then later you can adapt the model to different problems. So it's good, but
exactly. I think that if you look at challenges to build foundation model, definitely compute resources is number one, and that's one of the reasons we partnership. That's not the only reason, but one of the reasons we partnered with IBM, because they were able to provide necessary compute resources for the geospatial foundation model, and we're actively collaborating with the ULIC Supercomputing Center, and obviously maybe at some point with you, with compute resources.
Yeah.
Sometime we have some. We're just scratching the surface right now in terms of foundation model for science. I think it will only grow.
Thank you. We have to conclude here. I just want to say that it was a pleasure to have you here, to have you both here. Thank you for this conversation. It was very nice.
Thank you for the opportunity. I think it's like I said at the beginning, it's a unique situation you are in, inviting all these global set of students. I think they're having a good experience, and always happy to support with IBM. And
thank you.
Yeah.
Thank you very much.
Thank you for having us.
Yeah.